So just another video on the equatorial mount, and specifically as it relates to tracking the sun on the equinox and also during the June and December solstices. Remember, the key points with an equatorial mount is this polar alignment angle, which matches the latitude no matter where you are on the Earth. And that means the mount is able to track objects in the sky using a single axis of rotation at a steady rate. And tracking the sun, that rate is a precise 15 degrees per hour all day, which means the mount moves 360 degrees in 24 hours. So from that position to another 90 degrees of rotation, it would take exactly 6 hours. And the second axis that we're going to look at is the declination. Now at the moment, that telescope is set to a position of 0 degrees declination, and that is where it would be on the day of the equinox if it was tracking the sun. In December, in the southern hemisphere, to track the sun, the declination would be 23.4 degrees that way. During the June solstice, again to track the sun, the declination would be 23.4 degrees in the opposite direction. So what we can see is that for the equinox, the December and the June solstice, all that really changes is the angle of declination. The polar alignment angle does not change. The single axis of rotation to track the sun does not change, and the rate of 15 degrees per hour does not change. So we know that on the day of the equinox, the sun's declination is 0, and on the June and December solstices, it is plus and minus 23.4 degrees. So what I've done here is set up 3 polystyrene balls at a distance from the point of rotation that gives us the correct declination angles. And because it is attached to the equatorial mount, by rotating that single axis, we're getting an accurate representation of the motion of the sun on each of those days. So here is a small equatorial mount, and I have 3 balls set up in the position of the equinox, the June and the December solstices in the southern hemisphere. Now this is oriented for Sydney, Australia, and it's currently set at the position it would be in at 6 AM local time. Now on the day of the equinox, we know that the sun rises 090 all over the Earth. Now this mount would be oriented so that this direction is north, which means 90 degrees to the right, we're looking at east. And I have deliberately positioned those 2 drawers with a slight gap to simulate the position of east. I also have a small Bluetooth run cam, which is transmitting video to that iPad. And if we just zoom in on that, you can see the footage from the run cam, which I'll play also in this video. Now, as we can see, at 6 AM, the sun is just rising at 090 degrees. Now, if we go to the June solstice, we have the sun, which is now this ball here, just rising at a later time. So you can see the mount has had to move further past the 6 AM. And what we also see is that the sun is rising well north of due east. If we look at the December solstice, there's the sun rising. It is now south of due east, and it is occurring well before 6 AM. You can see the angle there. So what we see from this demonstration is a number of points that we observe in the real world. We know that in December, in the southern hemisphere, the sun rises earlier than 6 AM, and it rises south of due east. And we can see that from this demonstration. At 6 AM, local time, on the equinox, the sun will rise directly 090. And we can see that occurring like that. In June, the sun is going to be rising after 6 AM and north of due west. And this simple model simulates that perfectly for all positions. What you will notice is that for every sunrise, the angle of rotation is the same. The mount is rotating on a single axis and it is moving at a steady 15 degrees the whole time. So let's now take a look at the footage from the run cam that was attached to the mount. And firstly, we're looking at the sunrise. And remember, this gap represents the direction of 090 degrees due east. We're in the southern hemisphere, and this foam ball represents the declination of the sun during the December solstice. The center ball represents the declination of the sun on the equinox, and the one on the left, the declination of the sun during the June solstice. Now, as the sun is rising in December, clearly it will rise earlier than on the equinox or in June, and you can see that the position it is rising is to the right of due east, so it is south of due east. On the day of the equinox, the sun will rise 090 degrees, and in June it's going to rise at a later time and well north of due east. And you can see this demonstration very clearly shows that. So you can see that regardless of the date of the year and the declination of the sun, this equatorial mount will be able to track the sun using a single axis of rotation at a steady 15 degrees all day as the sun rises, moves through local noon, and then continues on to set. It's the same axis of rotation on the equinox in June and December. All that changes is the angle of declination, not the polar aligned axis. And the reason the polar aligned axis does not change is because that is aligned with the Earth's rotational axis. And it is the tilt of the Earth that results in the change in the declination angle of the sun. However, that single axis of rotation is all that is required to track the sun all day with an equatorial mount. So I now have the mount positioned as it would be at local noon, and as you can see, the location of the sun is quite different at various times of the year. You can see clearly from this demonstration that the angle of the sun on the day of the equinox is obviously going to match the latitude. Sydney, south 34 degrees latitude, is going to have the sun 34 degrees from vertical on the day of the equinox. And you can see clearly why that is the case. In December, the sun is going to be much higher in the sky, and we're going to have a shorter shadow than we will have in June. As you can see, in the June solstice, the sun's angle in the sky is going to be much lower, and that will cast a longer shadow. And there's the geometry. And remember, once again, it is always moving on the same axis of rotation. So I now have the mount turned around in the opposite direction, allowing me to demonstrate the sunset. Once again, those draws represent the local horizon, and the small gap represents a direction now of 270 degrees due west. That is the direction the sun will be setting on the day of the equinox. Anything to the right of the gap is north, and anything to the left of the gap is south of due west. You can see once again the mount is rotating on a single axis, and if we look at the iPad, I'll just have to adjust the contrast slightly. If we look at the iPad, and I'll play the footage in real time also, you will see that as the sun is setting, obviously in June, the sun is going to be setting first at an earlier time and north of due west. On the day of the equinox, the sun sets directly west, and during the December solstice, the sun will be setting at a later time and south of due west. You can see once again, just that single axis of rotation is all that is required. one axis of rotation accurately demonstrates the sun setting at various times of the year. You can see the geometry very clearly here, and that is what matches reality. So now we're looking at the demonstration of the sunset, which means to the right of the frame is north and to the left is south. So as the sun is setting, we're going to see that the ball on the right hand side, representing the June solstice, is setting first, and it is setting north of due west. On the equinox, we see the center ball setting directly due west, 270 degrees, and then in December we're seeing the sun set well south of due west and also at a later time. So that's why we get the shorter days in June, approximately equal day and night on the equinoxes, and longer days in December in the southern hemisphere. The whole time the mount is moving on a single axis at a constant 15 degrees per hour. So what I have done now is just tilt the mount to represent a much higher latitude than Sydney, Australia. In fact, it's closer to about 60 degrees south latitude. And what that means is, as the mount tracks on a single axis, the sun is moving horizontally faster than it is moving vertically. And this final clip is where I angled the mount to represent a latitude much further south than Sydney, Australia. And you can see, because of the angle, as the sun is setting, it is moving horizontally more than it is moving vertically as it sets. And that means it changes the angle quite significantly from the time the bottom of the sun hits the horizon until the top of the sun hits the horizon. Now this also explains why the further we are from the equator, the shorter the days are in winter and the longer the days are in summer, and also why time and date will show us a number of small anomalies with the sunset angle around the day of the equinox. So firstly, as the sun is setting, once again, during the June solstice, the sun will set first. During the equinox, the sun will set 270 degrees. Now remember, the geometry of that is the center of the sun as it passes horizontal. So I've tried to align that as best as possible. Looking at the stick going into that foam ball, that's the center of the sun, and you can see it is now in line with 270 degrees. As the sun continues to set, you can see that it is moving horizontally faster than it is moving vertically. So by the time the top of that sun disappears, it is now no longer in line with 270 degrees. And anyone that has studied time and date, particularly at high latitudes, will know that you don't always get the sun setting at 270 degrees exactly on the day of the equinox. Now this is actually more confirmation that we live on a globe, because it is this motion of the sun which can be tracked on a single axis, and the fact that the geometry of the equinox is based on the center of the sun passing horizontal, and the time of the sunset is the top of the sun passing the horizon, that causes that anomaly or that difference in the angle of the sunset. As we continue, you can see that in December the sun is now setting a lot further south, and because the sun is moving horizontally faster than it moves vertically, the daylight hours are going to be longer the further south we go in December. So once again, as I have been saying for a number of years now, the equatorial mount and the equinox sun angles absolutely prove that the Earth is not flat. The geometry of what you have just seen is what we observe in reality, and it cannot work on a flat Earth. The equatorial mount and the equinox sun angles combined are absolute confirmation that we are living on a globe. Now, I would always rather help somebody than insult them, but if you're a flat earther and you still don't understand the equatorial mount or the equinox sun angles, then all I can say is you clearly have a disability with geometry, because this geometry is not that difficult to understand. If you read through the comments on my previous videos, most people understand it very easily. If you're a flat earther and you still don't get it, then you probably need to get some help and try to understand why you struggle with such basic geometry. The equatorial mount and the equinox sun angles absolutely demolish flat earth, and if you don't understand why, then you have a problem with geometry.